Greetings, Astrophiles. This is Pat Cosgrove, and I'd like to welcome you to Cosgrove's Cosmos. This is a companion to my main website, cosgrovescosmos.com, where I document my journey into astrophotography covering images, gear, tips, and techniques. Today, I'd like to talk about an exciting new tool called the BlurXTerminator by RC Astro. The BlurXTerminator harnesses the power of machine learning to take deconvolution to a whole different level. In this video, we'll explore what it is, how to use it, we'll talk about the technology it's based on a little bit, and finally, we'll talk about some of the pushback that it's received. Let's get started. This video is a companion to a much more in-depth article that I posted on my website. The link to this article is going to be available under the fold. Let me start off by saying, as I was learning astrophotography, deconvolution was one of those things I had a very difficult time learning. It took a lot of effort and a lot of trials and tribulations before I got to the point where I could consistently get good value from the deconvolution tool that you can find in PixInsight. After I had begun to master deconvolution, I decided I would try to share my learnings in an article that I would post on my website. As I began to write it, it got so long that it was just too much for one person to deal with in one sitting, so I ended up breaking it into a 7-part series, which I posted about a year ago. Even this wasn't enough. I ended up doing 2 follow-up posts, one that talked about using easy decon and another that talked about using the regularization parameters to protect low signal areas. With 9 total articles now, you can tell that there's an awful lot that you need to know and you need to learn if you're going to use PixInsight deconvolution successfully. Then I heard that RC Astro had released a new tool called the BlurXTerminator, and I was pretty excited by that. So why was I instantly excited? That was because I was a customer of a couple of their other products, the Noise Exterminator and the Star Exterminator. Both changed how I do my processing. Both were also based on machine learning and a neural network approach. And finally, both kept improving after initial release as new learning and new weight tables for the neural networks were distributed. So I have to say, before even trying BlurXTerminator, I was pretty excited to see what this tool would turn out to be. So I downloaded a trial copy and I tested it out. And I got to tell you, I was blown away by what I saw. After trying out the BlurXTerminator, I mentioned to my local astrophotography friends that even though I had written a 9-part series on deconvolution, I felt compelled to write one more to try to wrap things up. I proposed that this new article would have one line, and the line would say, quote, "Remember my 9-part series on deconvolution? Well, forget all that crap. Just go out and get BlurXTerminator. The end." At any rate, I ended up writing my 10th and hopefully final article on deconvolution, and it turned out to be quite a bit longer than the one line I had originally proposed. So without further ado, let's talk about BlurXTerminator in a little bit more detail. So what is BlurXTerminator? It's basically an AI neural network tool that provides a new way of doing deconvolution. It offers many benefits. It takes a lot less time and effort to use. There isn't as much you have to learn in order to use it successfully. It has simple and very intuitive controls. It gives you a great deal of control not only stars, but also their halos. It provides the ability to do a differential PFS across the frame, which is something that can't be done in the traditional deconvolution. And then finally, it has the ability to correct stars that have been distorted by various factors. Let's take a look at its control panel. There really isn't a lot there, and most of the terms are set up with their default values. What if you were just to use this tool with the default parameters, something you would never do with regular deconvolution? Let's give it a try. I have my linear luminance image from my Malot 15, the Heart of the Heart imaging project. So let's take a look at it. I'm going to show you the first image here, which is the image that has had a slight bit of processing done to it, in that we've done the dynamic crop, we've taken out gradients with DBE, and that's about it. And the first thing we're going to do is we're going to do traditional deconvolution. When I originally did this project, I had a hard time finding the sweet spot in the parameters to get the best result that I could. And I was a little disappointed in the results. I don't think I got as much sharpening as I could. But as you look at the image here, you can clearly see that I have brought some benefit here from using the standard deconvolution. The stars are smaller, and certainly the nebulae is a little bit sharper. Now let's try the default parameters with BlurXTerminator. It looks great. It's dramatically different. The stars have been reduced much more. They're nice and sharp and tight, and the nebulae is much sharper. Let's keep in mind that it took about an hour of fooling around to do it with the traditional deconvolution. This one, I didn't do anything. I opened the control panel, I used the default terms, and I ran it. Now, it is true that it takes time to run. I have a 12-core Ryzen processor in my imaging workstation, and it took about five and a half minutes to run. So that part's a little bit slow, but I saved so much other time and effort that I was just delighted. I was very happy with the kind of results it was producing. When I think about how much effort I put into learning deconvolution and what I had to do in order to get reliably good results from that tool, I'm kind of blown away by what kind of result you can get by using the default parameters for a brand new tool. I think this is a breakthrough. Why don't we take a moment to take a look at the BlurXTerminator control panel and examine the parameters and the controls it offers. And the first thing you see is that there really aren't too many controls on here. It's a simple tool with a simple interface. There's three areas in here. We can talk about selecting what AI we're going to use. We can talk about the stellar adjustments, and we can talk about non-stellar adjustments. And then there are some flags you can put on that are convenience items so that when you run the tool, it runs in particular modes. Let's look at the Select AI button first. When you push that, you'll get a file dialog box opening up that allows you to choose the weight map that the AI is going to use for its execution. Like all smart tools that use a neural network, the weight map is what really defines the performance of the tool. And here I have several. I have version 1, which is what came when I first bought the tool, and I've already gotten a version 2 that's been out. So with just a few weeks' time, there's already been an improvement in the performance delivered. And I expect that over time, we'll see a series of these released, each one providing an incremental enhancement to the execution and response of the tool. Next section has to do with stellar adjustments, and we have two areas in here. We can talk about how we sharpen the stars, and we can talk about how we sharpen the halos. Personally, I love the idea of having this control split up so that I can adjust what's happening at the core and I can adjust the halo separately. It gives me an awful lot of control of what my stars look like. And I like that kind of control if I'm dealing with things like a globular cluster where the stars are all clustered together. I can get a feel that I want. And that might be a very different feel than what I would get if I was dealing with a typical nebula image. So having that in there is great. The other thing is to keep in mind that halos often carry the most color for the star. The cores of the stars are often bright and desaturated, and you don't see a lot there. They might even be clipped. But the halos will transmit a lot of the color. So you may want to adjust those differently for the particular image you're going after. Now the sharpened stars has a default value of 0.25, but it goes all the way from 0 up to 0.5. And there's a simple way to think about this. This is the fraction of what can be reduced for the stars found. Basically, it will try to reduce the star size by half when you're at the highest level, or it'll do it by a quarter if you're at the default. And if you want all the way down to 0, it's not going to reduce the stars. It's not going to sharpen them at all. The halo command starts at 0, where it has sort of an average amount of halo. But as you drag it over, it has a range from -5 to +5. And basically what it's doing there is just enhancing the outer shell of the star or sharpening it more. And this is something you can experiment with. I've found that the default values work very nicely, but you may want to experiment with this to get the look that you want to get. The next section has to do with non-stellar adjustments. In the normal mode, the default is automatic PSF. In this mode, when the tool runs, it's going to look at 512 by 512 tiles across the image, and it's going to determine the PSF based on the stars in that particular area. That measure will drive what level of sharpening is going to be done for the non-stellar areas. And most of the time, this is the right thing to have checked in there. However, you might have images where this is not doing as well. Think about long focal length images, or think about images that just don't have a lot of stars in the field. If you don't have a good sampling of stars in that 512 by 512 grid, you may not get the best estimate. If it doesn't have stars, it tries to determine the PSF from the non-stellar elements, but this sometimes can be not as robust. And because of that, if you have an image that's giving you problems, you can turn this off, and when you turn this off, you have two controls. You can manually put in the diameter of the PSF in pixels that you want, and this has a range from 0 to 8, with the idea being that a well-sampled star with 8 pixels across is doing pretty well, and anything beyond that is oversampling. And you can dial in whatever a PSF you think will work best with your image. One way you might do that is look at the stars that you do have in the image, try to determine their diameters, and then use that as a setting here. Frankly, I'd really like to see them offer some star statistics on sizes on this panel when you're in the non-automatic mode. That would be kind of nice to have. And that would give you a little bit more to determine how to set this control. The other is how much sharpening you want done. You basically have from 0 to 1, and 90 being the default. This is basically saying take the star and try to diminish it to 0, and to a point, if you will. And at 0.9, we're saying take it 9/10 of the way there. If it was at 1, you'd try to drive it all the way home. Now, in practice, it never gets that far because it's limited by the low contrast information that exists around the star. And if the information isn't there, then it will only go so far. But that's the intent here. And most of the time, you're going to want this pretty high. But this is something, again, you're probably going to want to do a little testing, see what would work best for you when you're doing that. One thing to keep in mind is when you're in automatic mode, the star corrections for aberrations and tracking errors and coma and things like that are going to be applied as well, but you won't get those corrections if this is on manual mode. So that's just something to keep in mind. In terms of options, the correct only option says go through and look for the stars that are misshapen and circularize them, fix them. And if you do that and do only that, you'll come back with an image whose stars are now rounder and better formed. The second one says correct first. In this particular case, what you're doing is you're running the correct only followed by the normal BlurXTerminator run. And when you do this, in some cases, they suggest you can get better images. The other is a non-stellar and then stellar. In that case, it does all the non-stellar sharpening first, and then it takes a second pass and does just the stellar. And I guess in some circumstances, that can be useful there as well. The final one is luminance only. And if you're dealing with a color image and you check that, it will only do a luminance specific deconvolution. If you're already starting with a one monocolored image, a luminance image, if you will, then this flag really has no function and is ignored. So that's what you have to work with. They're pretty intuitive. The default values for most images do quite well. You can feel free to experiment with different parameters, but these are very simple and intuitive to work with, and you don't need to do a lot to have this tool generate some fine results for you. Now that we've been introduced to the controls that BlurXTerminator provides you access to, let's take a look at the ones you're most likely to be using and get a feel for what they do across the range. And what I'd like to do is take my image of Malot 15, the heart of the heart, and I'm going to show you what that looks like when I go through the full range of the Sharpen stars and Sharpen halo. Okay, we're going to start with the Sharpen stars, and the slider, the first value we're going to look at is 0.1. Then we're going to look at 0.2. Then we'll look at 0.25, remembering this is the default. And then finally, we're going to look at 0.3, 0.4, and 0.5. Now, as you go through that series, you may notice that the stars are definitely changing size, but sometimes you don't quite get a feel for what that is doing. So let me go back and just jump between the two extremes so you can see what you can dial in. So we're going to go back, and what we're going to look at here first is the 0.1, then we'll look at the 0.5. And as you see the difference between these two, you can see that there's a much bigger change happening there, and that sort of bounds the range of what you can get. It gives you a nice clear progression, and the default works out pretty nicely. Now let's take a look at the slider for the halo adjustment. We're going to start at minus 0.5, then we'll move to minus 25, then we'll go to 0, which remember is the default. Now 0.25, and finally the maximum at 0.5. And again, to give you an idea of what range you just transgressed, we're going to go back to the minus 5 and go to the plus 5 to show you the extreme range. Again, I find these controls to be very intuitive to use. You can dial in just what you want. I'm pretty happy with its performance. Now what I'd like to do is explore a couple other performance aspects of the tool. One of the things it tells us is it does star correction. So I wanted to get a feel for what that was really doing. Now I have a Williams Optics 132 millimeter FLT APO refractor as one of my platforms. It runs at f7, and originally I had a smaller camera on it, and with f7 and a smaller camera, I didn't really need a field flattener. However, I recently changed that over to an ASI 1600 mono camera, and that's slightly different in that now I'm noticing that at the corners of my field, I am getting some distorted stars from aberrations. So let's take a look at that. The first one we're going to look at here is the upper left corner of the image, and you can see the distorted stars that we have here. Now we run BlurXTerminator, and you can see that the stars have cleaned up really quite nicely. They're round, well formed, and there's a definite improvement there. So BlurXTerminator did a great job on that. Now we're going to look at the opposite corner. This particular image is from the right bottom of the image, and you can see I have a very similar kind of distortion there. When we run BlurXTerminator on this, I'm seeing an improvement. I don't know if the improvement is as good as it was before, but it's definitely an improvement. So I think things are going in the right direction, and so that's pretty encouraging that I'll have some help with that particular problem from that particular scope. We're also told that BlurXTerminator works well cross-channel. In other words, it should do well when looking at a color image. It looks at the three color layers, and as it's making adjustments, it makes adjustments in a way so you're preserving what the typical color profile should be in a star as it goes from center to the outside edge. So I'd like to see what that looks like. I shoot mostly narrow band, so I'm going to go back and use my narrow band image of lot 15, and let's take a look at what that does with how that's handled by BlurXTerminator. So what I did is I created a linear color SHO image where I haven't done any color adjustments to it at all. So it has the typical color that you would expect to see from the first formation of an SHO image. We have, strong magenta stars, and we have green dominance over most of the image. But let's take a look at what happens when we run a default BlurXTerminator on it. It does a pretty nice job. It seems like it cleans up the image, and the stars don't seem quite as magenta and funky colored as I often get with narrowband. Now let's take a look at the same image, but I'm going to zoom in on a couple stars so you can get a little bit closer view of that. And here's the image before BlurXTerminator, and you can clearly see that, in the halos, we're getting a color gradient there that goes towards the magenta. And now the same perspective after BlurXTerminator is run, and it's looking quite a bit better. It cleans up quite nicely. So this is interesting because After doing this, not only do I end up with a sharper image and smaller stars, the stars have much better color and much more natural color, which saves me some work down the road. So it looks like I did a nice job in this particular instance. The other thing I wanted to explore a little bit was how it handled two other circumstances. I have one camera platform that's based on the ASCAR FRA 400 scope, and that also has an ASI 1600 mono camera on it. That camera is slightly undersampled. And we know when you have undersampled data, deconvolution doesn't do as well because you don't have good images of the stars and the PSFs are distorted. I wanted to see what it would do with that circumstance. The second thing I was curious in is what happens when you have a bright star and another star very close to it, such that their airy disks are very much overlapped. I wanted to get a sense for how it handled that situation where you had not just an isolated star, but two stars that had images that were interacting and overlapping. So I took this particular image from my FRA 400 scope, and if you look at this field, you can see in the middle a bright star with a smaller star impinging right on its side. And if you look around at some of the fainter stars, you're going to notice they're undersampled, and therefore they're a little boxy. And typically when I do deconvolution on images like this, the fainter stars become sharper, but they become boxier, which is not necessarily a good thing. And I wanted to see what BlurXTerminator does in this particular case. And what it does is it definitely does a good job, as you can see here, on the overlapping stars. I think that's a very natural output. But you can see that the undersampled stars are sharper and they're still boxy. So the tool is not trained to handle that particular circumstance. I think this tells me that the better data you have going in, the better result coming out. And in this particular case, it really does nothing for undersampling. Maybe that's something they might try to tackle in the future. That'd be interesting to see if that's possible. But for right now, don't expect any relief from undersampled images where you have boxy stars. Okay, now that we've learned a little bit about BlurXTerminator, let's do a brief comparison between it and the traditional deconvolution tool that you would use in PixInsight. First, we're going to look at what the benefits are in terms of time and effort when using BlurXTerminator. One big advantage is that there's no need to prepare a PSF file before you even go into the tool. For that matter, there's no need to do any real preparation work. There's no need to go in and create an object mask to protect the low signal areas. Or if you're not using an object mask, if you're using the regularization parameters, there's no need to determine what the level of those should be in order to get the effect that you want. There's also no need to create a local de-ringing support image. None of those things has to be done here. You also don't have a circumstance where you're selecting previews on an image and you're iteratively going through and determining what the right parameters are in order to get a good effect and avoid artifacts. And finally, there's fewer controls that you really have to set. Quite often, the default parameters will do a good job for you. Next, let's talk about the power of BlurXTerminator when compared to the traditional deconvolution tool in PixInsight. The first is the fact that it can fix stars. It can circularize stars that are distorted, either because of guiding, aberrations, or coma in the system. If there's something that is causing your star to be out of round, it can go in and actually fix that. And that's something that the traditional tool cannot do. And because of that, it can deal with PSFs that are distorted, either in terms of shape or truncated. And again, that's something that the traditional tool really can't do. Another thing that I find very powerful is the idea that each 512 by 512 grid in your image basically is going to end up with a tuned PSF just for that region. You have a differential PSF across the frame. This is great because if you do need a different situation in the center of your frame versus the edge of your frame, which is pretty traditional in most optical systems, you can have something with BlurXTerminator which adapts to that, and the traditional tool cannot do that. Another advantage is that BlurXTerminator can work with a color tool. It can work cross-channel. When it looks to optimize a star, it looks between the three color layers and makes sure they're optimized to give a good image of that star when deconvolution is applied. And again, that's something we don't get with a traditional tool. And finally, I think that the intuitive controls that allow you to tune how things are sharpened from the core of the star to the halo of a star, and in a very intuitive way, is also a big advantage. So are there any downsides to BlurXterminator? Well, yeah, I guess the first one would be the cost. This is not a free tool. It is one of the more expensive tools out there. And you have to really be able to feel that you can justify that cost. For me, the $100 fee was easy to justify when I think about the investment I have in both my equipment and my software and my computer systems in order to do astrophotography. This seems like a relatively drop in a bucket compared to all that. And the fact that it's doing something better than what I can do with a process that takes a lot of time, for me, it was an easy thing to justify. Next, I would say it's computationally slow. When I ran this on my image processing station, which is based on a Ryzen 12-core CPU, it took about 5.5 minutes to process a neutral image, one-color image. So that's kind of slow. Now, it is true that I have not gone through and set things up so that it's running on my GPU. And for people who have done that, it sounds like it speeds up quite a bit. But even with that, there is some computation that will have to be done there. It's not instantaneous. Another fact is while BlurXterminator is very robust and easy to use, it doesn't mean that you can't create artifacts with it or get results which are something you may not like. Depending on how you have things tuned, you can get into a situation where you can see some ringing and you may have to dial things back. So don't trust it completely. You need to make sure that you're still engaged in the process. Another factor is you may find that you're going to want to change your entire workflow in order to maximize the value you can extract. I know that's something I'm looking at, and I'll talk about that a little bit later. Another factor is if you're a person who takes great pride in their ability to use deconvolution to get better results, and you can leverage your skill and knowledge to do that consistently, your ego may take a hit because suddenly here's a tool that not only is likely to do a better job than what you can achieve, but that means almost anybody can do that. And finally, this tool may not be suitable for those who are doing scientific work. It may be that traditional tools and their transforms are better known and give you a better circumstance for extracting scientific data from your images. If, on the other hand, you're doing this for the artistic sake, you're really trying to process your images, maximize the quality you can achieve with the data you collected, then I don't think that is as big a concern. Let's talk for a minute about workflow considerations when using the BlurXterminator. I've shared in several previous videos what my preferred workflow is when working with narrowband SHO images. Let's take a look at that here. In this particular workflow, I tend to create a synthetic luminance image by combining the HA03 and S2 master images. Then I use the luminance image as the start of a processing path that is focusing on sharpness and detail. So it's no surprise that once I've created this synthetic luminance image, this is where I typically have done my deconvolution in the past. At this point, I would move forward to the nonlinear processing realm with a stretch, and it's there that I first create my color image, my color SHO image. Then I jump into a starless workflow where I maximize the quality of the nebulae in the image, process the stars separately, and then combine everything back together. So if I was to use BlurXterminator, how would I change this? Well, I don't have to change it. I could just use this same exact flow, and I could apply BlurXterminator onto the luminous image right where I do it today, and I wouldn't have to change anything. But I think I might lose an opportunity if I were to do that. I think there's an opportunity here because BlurXterminator is really working well with cross-channel. There's an opportunity to do something a little bit different. So here is a way I'm considering modifying my workflow. In this workflow, what I'm going to do is I'm going to create my color SHO image back in the linear domain. And now that I have my first color image, this is the image I'm going to use to run the BlurXterminator on. This should give me the advantage of optimizing the 3 color channels around the star structures. From this, then, I would compute and extract my luminance signal, and the rest of the processing path would be done just as I did before. By the same token, I would take the linear color SHO image, I would take it with a stretch to nonlinear, and then starless, and then I would complete what I'm doing. But I think the idea of creating my color image a little bit earlier and running BlurXTerminator on it, and then extracting a luminance signal from that, would give me the best circumstance going forward. I've done some experimenting with this. I'm pretty happy with the initial results, and I think this is going to be my workflow as we go forward for narrowband images. So now let's talk about what I do for LRGB images. Well, in LRGB images, I'm already creating an RGB color image in the nonlinear domain. And at that point, I'm doing color correction by using PCC or SPCC. Anyways, so I think how I would change that is very simple. Basically, I would apply BXT to both my RGB color image and to the luminous image, since it's a real image that came in through a different channel. Both of them, I think I would try to optimize using BlurXTerminator and then continue on with my normal processing. So how does BlurXTerminator do what it does? We know that it's an AI-based tool. We know that machine learning is involved, and we know this network that's created has been trained on Astro data to produce the right result. What does all that mean? Well, in my more in-depth write-up on my webpage, I go into some detail to give an introduction to this technology, just high enough level that you get a feel for what's going on. For the purposes of this video, I think I'm going to do this in a very truncated way and encourage you to go to the web listing if you'd like to learn more. So what I'm going to do is I'm going to jump to my web page, and I'm going to talk through a couple of charts that are in there to give you a very high-level feel for what this technology looks like and how it works. So now we're looking at my website, and the first thing I want to talk about is the fact that all of this learning technology started with this concept of neural networks. And neural networks are a software construct that were inspired by the structure of the human brain. We think of the brain as being consisting of a series of neurons that were networked together, and we have this idea of one neuron, when it fires, sends a signal to a network of other neurons which may fire because the first one fired. So in software, a neural network tries to emulate that. But the first thing we have to start with is a neuron. So a neuron is just a node that holds a value between, say, 0 and 1. You may have a series of inputs from other nodes coming into it, and these are connections. And the connections are stronger or weaker depending on the training. And what makes those connections stronger or weaker are the weights that are applied to each connection. And when the neuron is really doing its job, it looks at each connection and what value is coming through, multiplies it times the weight, and sums those up. And then based on that sum of all the signal it gets, it will kick a signal out to the next neurons down the chain. So in order to build a network, we know we have these neurons, and we know that we're going to put them together in some form. And so down in here, we sort of have this generic form of a neural network. And basically, we have one column of neurons representing a layer, and each network has at least 2 layers. It has an input layer, and it has an output layer. And the input layer are a series of neurons that hold the values that are pertinent to whatever it is you're trying to compute. Let's say that you had a series of predictors about an image and you're trying to classify it into some kind of image, whether it's an indoor image or an outdoor image. You would load the predictor values in as many neurons as you needed to represent those inputs. And then you might have maybe 1 or 2. Let's say you were trying to detect whether it was an indoor or an outdoor picture, for example. There's 2 states that you might get. So you might have 2 neurons on the output. Then you can have other layers, an arbitrary number of middle layers that are called hidden layers, and they can have an arbitrary number of neurons. Now you need to lace these all together. Every neuron is connected to every other neuron in this form of network. This is a fully connected network. And so if we want the network to do its job, we would load these first neurons with the predictor values that we want, and then we would start to compute the values for the next layer. And when I look at this first neuron in this hidden layer number 1, if I want to know what its value is, I look at the signal for every neuron that came before it in the input layer, and I multiply that by the weight on its connection, and I sum it up. So this contributes its value times a weight over to this neuron, and then this one contributes, and this one contributes. So this is the sum of all the input values times their individual weights. Then it will feed a value forward, and the next network will work in the same way. And so what happens is you have a feed forward network. You load in the inputs, it goes through, and all these multiplications are being done. And at some point we get to the output nodes where you're summing up the last bits, and then we look to see what these values are. Now remember, the values are between 0 and 1, and the one that has the highest value in it is activated, and that would be the classification that you want. So that's kind of a simple overview of what a network looks like. Let's look at an example that might make that a little bit more real. And this is a classic example that's often used for talking about training neural networks. Imagine you were trying to take handwritten digits between 0 and 9, and you wanted to be able to recognize what those digits were. So we could create an input that's 28 by 28 pixels, and each of these pixels has a value between 0 and 1. And we could create a simple network that tries to do this particular problem. On that one hand, we have the tile that represents each individual written value. And that's a 28 by 28 grid. So that's a total of 784 pixels. We would have one input neuron for every one of those pixels in the grid. And we know we're trying to classify this into one of the digits, so the output would have a node that would represent each of the digits. In this particular case, we're just going to do a very simple example where we'll have one hidden layer, and these are all going to be fully connected. So when we want to test this network out, we want to use this network, we would load the values in, we would compute the values forward, we'd look at the final values in the output node, and the one with the highest value would be the classification of what we wanted it to do. So whether this network works or not is based on the weights that we put on each of these connections. Well, how do we get those weights? Well, those weights are gotten through a learning process. And in order to do that, we need to have a population that we're going to be learning from. In this particular case, I can come up and I can have many different samples of different people writing each of those digits. And so I could create a population that's very large, that is sampled, digitized handwriting from many, many, many people who are writing these digits. So I have all the different variations from that. So that gives me a sample of inputs, and we want this population for training to be very large. The next thing we want is we need ground truth. We need to know what the right value is. So someone would have to go through and say, for all these values, the right answer is I want a high value here, 1, and I want low values for everything else down here. I want it to tell me that that was digit 0. So basically, you have this large population that you're exposing to the network, and you're telling the network, when you see something that looks like this, I want you to give me an output that looks like that. Well, somehow we have to take that data and we have to learn. And one of the ways we do that is we create what's called a cost function. It basically would look at any given answer and say, how good is the answer? How close is it to the ground truth? And once we have that function, it's really an error function. What we can do is we can start with an initial configuration on the network. And what we're going to do is we're going to take all these weights. We don't know what these weights should be, so we're just going to load them in with random numbers. It's completely random numbers. And now what happens when we're loading the input in and we multiply this out, we're going to have a very bad network. It's going to do a horrible job. It's going to do a random job. But that's okay. We'll load it in the very first time with random weights. We'll push all the values in, we'll calculate the answers, and then we'll calculate an error from each one. And we'll look at some measure of error, the cost function. And what we're going to end up doing is the learning process will take a look at what the answer it got, the answer it wanted, and it'll look at these networks for each of these nodes, and we'll figure out, how can I nudge these weights in a particular direction so that I seem to be getting an answer that's closer to what I want to get. And it would do some kind of nudge for every one of these weights for each of these nodes going forward. And then, in fact, once it's done that, it will propagate this backwards and do the same thing, working in the reverse direction until we get back to the final set of weights that we want to nudge. So this is called back propagation learning. And we're basically really nudging the weights around in a direction that seems like it would be better. And one training run of the network, I might nudge the weights so that's not quite as horrible as it was before, but it's certainly not final. But imagine I have a very large population, and imagine I ran this over and over and over and over and over. The first time you run it, the way you would change these weights could be relatively large, but at some point, you've gotten an answer where there's no more nudging. You can't find a lower error very easily. And so we begin to converge to an answer. And that's what we mean when we talk about training for a network. We're going to have a set of input values. We're going to have ground truth for those inputs. We're going to feed that through a network. We're going to have a cost function that tells us how good we did. And then based on that cost function, we'll look at how we would nudge these weights in one direction or another that would put us in the direction of goodness. And if we do this well enough, we can train this network so that it'll have a total success rate that can make us more successful. So that, in a nutshell, is a real high-level, very high-level overview of neural networks. And I should say that we're not really using neural networks when we're talking about a problem domain like what BlurXTerminator is likely to be doing. There are new flavors of neural networks called convolutional neural networks, and I talk about that in the main write-up. Convolutional neural networks add additional layers in where things aren't fully connected, and the difference from going from the input to the next layer is being able to do various convolutional kernels, which create features. It creates a feature map for a particular image, and then the feature maps are what is fed into the network, and we do the training that way. So we're pretty sure that RC Astro is using some version and some architecture of a convolutional network, and but regardless of that, the basic idea here is still the same. So what is it that they are doing? So they've created some kind of architecture of a convolutional neural network. Then we have to do some training, and we know the training is on Astro data. What might that training be, and how might it have worked out? Well, we know we need some input data that are Astro images. Well, one could imagine that they got a sample of images of various objects and various parts of the sky taken with different combinations of telescope and camera. And one can imagine different places where they might have gotten that. And so that constitutes their input data. What about their ground truth for training? How do you get to an image that says this is where you want the image to end up? This is what it should look like. Give me an example of an image where deconvolution has been run really successfully, and it gives me what I'd like to get out of that neural network. And how would you do that? We know from their documentation they're using data from the Hubble telescope and from the James Webb Space Telescope. But how? I think it might go something like this. If you had images taken with the Hubble or for the James Webb Telescope, you have images that, number one, have no atmosphere in the way, which is a big contributor to what we're trying to compensate for when we're doing deconvolution. We also know that they're not going to have the same kind of guiding errors that we have here on Earth, and that the guiding should be very good. So they're less likely to have those kinds of errors. We also know that the telescope systems are very high precision, certainly more precision than what I can put out in my driveway. So again, we have telescopes that have extremely high quality optics, and more importantly probably is that the optics are well characterized and compensated for. And we have a data set where the astrometrics are known, and it's in the public domain. I can imagine a scenario where you have a population of information or images from amateur telescopes where we can do plate solving to figure out exactly what the locations are. And then we can map that up with data taken from one of these satellite telescopes and treat that as the aim. Additionally, we know that they work in tiles of 512 by 512 across the image. One could imagine that I could take a population of images of random telescopes and cameras and the Webb telescope, for example, a Hubble telescope, and then break those into little 512 by 512 imagettes, and each of those small images are something that I could use for training. I think that RC Astro is doing something like this. I've greatly oversimplified it, but I just want to give you a sense of how one would create a training population along these lines, how one would create a network that is then trained to that data. And at the end of the day, you end up with a neural network that when you feed in pixel values, it'll come out with pixel values, which are a transform of that, which is trying to model and account for the atmospherics as seen in features that are extracted in the image through a convolutional network, which are fundamentally stars or PSFs. I think most people don't really have a good understanding of what machine learning is, or what it does, or what it can do. And I think there's not only misunderstandings, I think there's mistrust of that technology because it's new and it's not something that's been around for a long time. And I was a little surprised when looking at the feedback around the BlurXTerminator on the internet. I saw a lot of really positive statements, but I saw a lot of other concerns being raised, and I thought it might be useful to spend a few moments just looking at some of the things that I was hearing and give you my take on it anyways. The first is this idea that somehow the tool is replacing your pixels with someone else's pixels, or maybe pixels from the Hubble Space Telescope. And that's not what's happening here. Basically, the training data is allowing the network to train and emulate a deconvolution function. And as such, it's transformational. We insert our pixels into the front end of that network, and they're operated on as they go through the weight network to be transformed into a set of pixels which should be sharper. Basically, that's just a function, and that's all that a normal deconvolution is. After we set up all the parameters, it's a transform. We plug in values, and they're transformed in place into values that we hope will look sharper. And so this is just a different way of doing that, and there's no way that pixels are being substituted or there's something nefarious going on there. I mean, you think about it, where would they get those pixels? If you'd have to be able to get up to the cloud to get the pixels, and this tool will run if you have no internet connection. Yeah, you do download a weight network in order to run the tool, but that's not a sufficiently large database to have, all the pixels for every object at every scale in the sky so that you could do a substitution. So that one just isn't true. I think that's just a misunderstanding of, the training process and how the technology works. Another concern I've seen is that there's a fear that this machine learning technology is creating sort of this one-button fix. Instead of doing all of the skilled image processing that we do to create an astrophoto now, are we going to have a situation where any Tom, Dick, or Harry pushes a button and you get this perfect image out, and we've lost something from astrophotography? I don't see that happening anytime soon. This kind of training is usually good when you're trying to go after sort of a one-dimensional problem, if you will. Like in this case, we're looking at deconvolution. In previous cases, we're looking at star removal, or we're looking at noise. I think this kind of technology works really well when you have a wealth of input data and you have a very narrow scope of what you're trying to operate under. I think it would be really, really difficult to try to create something that would be a one-button push. I've always maintained that if you had one set of data and you gave it to 10 astrophotographers and asked them to process it, you would come back with 10 images that were very different, probably very good, but each would be the vision of each astrophotographer and how they do their processing. Their signature look would come through. So think about a training data that was going to be a one-button fix, right? You could have the same training data coming in as inputs, but there are so many outputs which are valid outputs. How would you get any ability to do that? And If there was a one-button tool, I know I would insist on having overrides and controls that would shape what it did to match my vision, a way I want my images to look. I wouldn't use such a tool. So I don't really think that what we're looking at now is close to doing that kind of thing. And I don't know if something like that could ever happen, and I'm not too concerned about it. I think another concern that I've heard is that BlurXTerminator encourages sloppy data collection. Why bother tuning your telescope to have nice flat fields? Why worry about getting perfect guiding down? Just do the best you can, slap it together, and if there's guiding errors or if there's nonlinearities or aberrations, well, this will come along and fix it, and therefore you don't have to be careful about getting good data. Well, in my own testing, I've already shown some examples where the better data you've collected, the better job that BlurXTerminator will do with it. And I think that's always going to be true. If you end up with some images that have problems in them, it's nice to have a tool that will mitigate some of that problem. But it's not likely to mitigate all of the problem. And if you came in with more pristine data, I think that will allow it to get a better result. And so I really don't think it's valid to say that this encourages sloppy data collection. I think people who are doing astrophotography are serious about it. As they become more experienced, they pay attention to finer and finer details because they realize all those little details sum up to give the final quality of the image, and they're trying to eke out the best they can from what data they were able to collect. And I think that that will always be a motivation for advanced astrophotographers. And I just don't see having a tool like that making people lazy. I think if people become lazy and depend on a tool like that, they have a crutch and they'll never be able to progress very far. At least that's my take on that. Another complaint that I have run across is that people don't fully understand what the AI tool is doing, and they're not sure if they trust it. Do they trust this thing to do the right actions in all circumstances? And given the fact that neural networks can become quite large, the weight networks can get so complex that nobody can understand exactly why the weights are split up the way they are and how it works. There's no such thing as debugging a neural network. Either you train it and it does well, or it doesn't do well. But does it do well consistently in all cases, and can you trust it to do well? That's a pretty valid concern. If you're not familiar with the technology, it seems like it's too good to be true. I can see people who would have a concern that somehow it is distorting the data or doing something that it's not wanted. I think that's a valid concern. I think there's a case, just like any tool. If you have a tool that is trying to solve a problem in imaging and it's a complex tool, whatever method is used, whether it's a neural network or it's a linear model or it's a statistical classifier, whatever you use, it's going to try to do its job. It's going to try to solve a problem, and it's going to have some error rate. And the question is the nature of the error something that you like and you can accept? And I think any tool that comes along that takes on these big problems, I think it's up to the astrophotographer to try it out in a lot of circumstances and decide if this tool is doing what they want it to do. Are they happy with what it's doing, and are you creating pixels in a final image that represent your vision for where you want to go? I think that's something everybody has to decide for themselves. And if some people don't like the philosophy or even the performance of these kinds of tools, and they want to go a different way, that's great. That's what makes astrophotography really interesting, and that's what makes you when you make your processing choices. So I don't think there's anything wrong with wanting more experience and proof with a tool before deciding to adopt it. That's a pretty reasonable concern. But I can say that I had another tool that I did a deconvolution with. It was the Fix and Sight deconvolution tool, and it often did things that I did not like, and I had to just take a lot of time and effort trying to rein that in and try to make sure that the result I got was a good result that looked natural and that I was happy with. And it took a lot of time and learning and experience to get to that point. When I use the BlurXTerminator, I don't have that learning curve. I like what I'm seeing so far. That doesn't mean I may not, and someday I may see some bad artifacts coming out of it. But so far, my experience has been very positive, and with little prior knowledge and training, I was able to use a tool to get what I saw as a really nice result that was easily modified with a very intuitive set of controls. And to me, this was a value. And, I think that a lot of people who have used deconvolution and depend on deconvolution will try this and probably one way or another begin to work that into their own workflows. I'd like to thank you for taking some time with us here today on Cosgrove's Cosmos. I hope this video has been informative and interesting. And as always, we welcome your questions and comments both to this channel and to the website. Please consider subscribing and ringing the bell, and that way you'll support the channel and you'll be made aware of any new content when it comes along. So this is Pat Cosgrove signing off for Cosgrove's Cosmos, and I wish you clear skies and excellent seeing.